Alrighty, folks, sickles, we have a very important video to do today. This is the contents of chapter 15. We skipped 14, and chapter 15 is on simple harmonic motion. And in order to save time, I'm going to abbreviate that SHM from now on. And as you can tell, this is one of my favorite topics in all of physics because it's named after me. When I give this lecture in person, what I like to do is I like to pace back and forth in front of the board as I give the lecture, and then later I see if anyone noticed that I was doing simple harmonic motion as the lecture went on. But I'll give you the skinny without the physical joke here. Harmonic motion is any motion that repeats with a regular period. In other words, it takes the same amount of time to go back and forth. And that could be everything from a pendulum that swings back and forth, or a ball that bounces, boing, boing, boing. Even though it bounces less each time, it takes the same amount of time to bounce up. It could be any of these things, any motion that has a regular period. So what makes something simple harmonic motion? Well, simple harmonic motion has some special stuff to it. Simple harmonic motion is described by sine or cosine. And also, simple harmonic motion has a restoring force. Ooh, I'm whistling. That is linear. President Obama used to whistle when he talked. It always, maybe I'm imitating that for some reason. Okay. So these two things, they actually go hand in hand. You can't separate them, but everything that has harmonic motion has a restoring force. That's why it repeats. So you pull a pendulum to this side, gravity brings it back to the middle, but then it overshoots to the other side. So there's a restoring force. The restoring force in the case of the bouncing ball, of course, is gravity. So if we have a restoring force that's linear, we're going to get a motion that is so smooth and perfect that it can be described by sine or cosine, which are the smoothest oscillating curves there are. Okay, that's what we're going to do. And we are going to learn this by studying the mass spring system. This is the simplest thing you can imagine building that behaves in this nice oscillatory fashion and goes back and forth with a regular period described by sine or cosine and has a restoring force that is linear. And so if you can study the mass and spring system and understand how it works, pay attention to all the steps you go through, then any other system can be studied by just following the same steps with slightly different numbers or reasons. So that's what we're going to do. Now, I need to sort out which of these. That's a good one. One of these black pens is a little smashed up and makes a big mark. I cannot tell. Okay, I'm going to treat them equal. We should treat all of our children equally. All right, so I'm going to use this area down here to kind of get us started. What is a mass and spring system? Well, first of all, we need a solid wall and a floor. And the floor cannot have any friction. Then we need to place a mass on this floor and mark the location of the mass as the origin. Then we connect a spring from the wall to the mass. That is the system. No friction with the floor, a mass, and a spring. And so how do you get this thing started? Well, you get this thing started by pulling the mass out away from its resting position to a new position. I'm going to mark that with the letter A. And that, of course, will stretch the spring. And when you let it go, the mass will return to its resting position, but it will now have velocity, it will overshoot the resting position, and then it will begin compressing the spring until it gets to a position minus A. And then the spring will be maximally compressed and the mass will stop. But the spring will now push it out, so it will go over here and return to its regularly scheduled equilibrium position, but it will now be moving in the other direction and it will overshoot. This is a graph of what's going to happen, or actually a drawing of what's going to happen to this thing as a function of time. This is a cycle. And I said that we started it here by pulling this to the side A, but you could actually start this in any one of these positions. For example, you could start with the mass at the origin and you could kick it towards the wall, and then it would do the cycle over and over again, starting from here. Or you could push it in next to the wall and let go, and it would go boingy, 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 going through this cycle. Now, there's a lot of things you can do with just this concept, just this idea, and this cycle. The first thing that we can do is we could talk about what's going on with the energy. This is a conservation of energy machine, and all of the energy is potential energy here because it is spring potential energy. We have a stretched spring. But here, when we get back to the natural length of the spring, we don't have any potential energy. It's all kinetic. It's all potential in a compressed spring here, and it's all kinetic in this drawing. If we were to stop somewhere in the middle, right here, we would have a mixture, of potential and kinetic, but the total energy would be constant the whole time. So this is a system where we are washing the energy back and forth between potential and kinetic, potential and kinetic. Actually, I should continue going around this way because that's what it does. Okay, what else can we do with this? Well, first thing we can do is we can address the elephant in the room. What is the meaning of this A? And A is the amplitude of the motion. In other words, A is the maximum extent away from the equilibrium position that this thing will get, both in the positive and negative directions. And with a spring, that's important because that's the maximum amount of stretch of the spring. So we could, if we were feeling it, we could I'm just going to push this up a little bit, bring another piece of paper down here. So we could kind of try to guess at what these curves look like. What would the position versus time look like? Now, in order to do this, I'm going to cheat a little bit here. Okay, I'm going to go ahead and make some dotted lines here. And I'm doing this all by hand, so it's probably not going to work out that well. Okay, so what is a good looking graph of the position versus time? Well, we start at an amplitude of A. We then return to the origin. We go to an amplitude of minus A. Then we return to the origin. Then we go to an amplitude of A again. Looks like we have a nice looking cosine curve. What about the velocity? What does the velocity of this cycle look like? Well, it's a little harder to think about. Certainly, the velocity starts at 0. And as you can see from this drawing, it starts at 0, but then it goes negative first. So we're going to go from 0 to a negative value, then back down to 0, then to a positive value, then back down to 0. This looks like minus sign. So we got cosine, we got minus sign. Let's do the acceleration. And I didn't put enough dotted pink lines here, but I could probably fake my way through this. All right, well, the acceleration, and now we'll look at this drawing. Acceleration, our first acceleration from here is to accelerate that way. We don't have the motion yet, but our acceleration is this way. We actually have maximum acceleration here and minimum acceleration here. Acceleration comes from the force of the spring. So maximum acceleration here, minimum acceleration here. So we're going to start with a negative acceleration, and then we're going to go to negative acceleration. Then we're going to go to 0. Then we're going to have a positive acceleration, then we're going to go to 0, and then we're going to have a negative acceleration. So smoothing this out a little bit, looks like we have a negative cosine curve. In fact, I think we could go right ahead and we could figure out what these things are. What do these things look like? Well, this one is pretty easy. X as a function of time will be the amplitude times the cosine of something. Something. Well, interestingly enough, this right here, from here to here, is the period. And we probably should say t equals period. How long does this take to repeat its motion? So we get from this position through all the other positions and back to here, we get to do that in one period. So we need this cosine to go through 2 pi in one period. And the way to do that is to take 2 pi and multiply by t over t. You see, by the time we get to a t of capital T, this is 1, and we've gone 2 pi. So there we go. I just, from this graph, from the shape of this graph and the fact of the period and the fact that the amplitude has to be a, I've just written out what the equation of motion is. And also, we need to remember that going from position to velocity, you're taking a derivative. And that's why we got minus sign here, because the derivative of cosine is minus sign. And the derivative of velocity is acceleration, so the derivative of minus sign is minus cosine. Within the skill of drawing that I have. Man, I really do envy math teachers. They are so excellent at drawing sines and cosines. And here I am with guiding markers and still producing stuff that looks like a 5-year-old did it. Anyway, we can either find the what am I saying? Parameters that make this graph work, or we could just take the derivative of this thing, right? Take the derivative. You're going to have v as a function of t, and it's going to be a. Nothing happens with a. Cosine becomes minus sine, and then we have to take the derivative inside of here, everything multiplying t, which is 2 pi over t. So a times 2 pi over t, and then times, I put a minus sign out front, sine of the same argument, 2 pi t over t. Okay, so forgive my little minus sign out front there. Take the derivative again, and we're going to have a as a function of t, and it's going to have a minus sign. It's going to have an a, and then it's going to have another factor, so that's going to be 4 pi squared over t squared, and cosine 2 pi t over t. All right, so I was able to know just about everything about this mass and spring system by drawing a picture, thinking about the energy. We could put equations to these energies if you want to do stuff like that too. Make a graph of the motion, figure out that it's going to be a sine or a cosine, and fit some parameters. I've got answers. I can plug things in and tell you where this thing will be next week and how much energy it will have and all kinds of stuff. Here's some interesting stuff we can do as well. How far does this thing move in one cycle? Well, it moves A again, A again, and A again. So the total motion during one period, one cycle, is 4a. That's how far it moves. And we also said on this diagram, we said that, hey, at this point we have the maximum force, we have maximum acceleration, we have minimum velocity, and we have maximum displacement. In this graph, we have no force, we have no acceleration, we have maximum velocity, and we have no displacement. So we can say things about these graphs or this picture, and we can get a lot done. But there is another way. There's another way to solve these problems, and it has got some advantages. It allows us to not do a whole lot of extra work when we are solving a new system that we've never seen before. So here's another way. Another way to solve this is to look at the forces. The force from a spring, when you pull it to the side, is minus kx. The minus sign is important here because, again, the direction is important. We saw that on the diagram before. So springs always pull in the opposite direction than you have displaced them, and they pull an amount proportional to their spring constant. That is if you have a linear spring, and many springs are linear for a certain part of their stretch, but not all of it. So this needs to go into Newton's law, F net equals m times a. That would mean that minus kx equals m times a. But a is the derivative of the velocity, which means it's the second derivative, time derivative, of the position. So when we put this all together, we get minus kx equals mass times the second derivative of x. Okay, let's get this constant to the other side with the other one. Minus k over m x equals d squared x dt squared. And this, my friends, is a differential equation. Differential equation because it is an equation that involves a function and its derivative. In this case, it's second derivative. If you wanted to be very correct about this, this is a second order, because it's a second derivative, linear, because the function is just a linear function, not squared or anything like that, a differential equation. We're going to solve a second order linear differential equation, and you will be able to impress your friends by saying the phrase second order linear differential equation solved. Okay, how are we going to solve this equation? Well, we're going to solve it using an age-old method, guess and check. We can make a guess at what the solution will look like. We can put a couple parameters in that guess and tweak those parameters until it works. So we have to ask ourselves the musical question: what function can I take two derivatives and get the function back with a negative sign? That's not really good English. For what function can I take two derivatives and get the function back with a negative? That's probably a better way to say it. But this is the question that I'm asking. And if we can guess at it, we can have the solution. Now, you already know the solution because we did solve this problem in a different way by inspection. But let's do it by this. Well, that is either going to be cosine or sine. That's the answer. So how many parameters would we need to put in this to be able to tweak things? Well, we need to put one parameter. I'm going to stick with cosine. We need to put one parameter out front. We already know this is going to be the amplitude, but that will be able to adjust the size of the thing. And then cosine. And now we need another parameter that goes along with the time, and we're just going to call it omega. Okay, what the heck is omega? It is an angular frequency. But for our purposes, it's just a parameter that we can tweak. The problem will actually tell us what it needs to be in order to make the solution work. And then what is that's just an amplitude of motion. And again, that's just a parameter. The problem, the conditions of the problem. And not only that, but the conditions of the problem will tell us whether we should have been choosing a cosine or a sine, or even something in between. You know, there is a generic way to put any kind of trigonometric function in there. What you have to do is you have to throw in an extra term, omega t plus some angle. They call it phi or phi or whatever, and that can be any function you want. If you move this forward to 90 degrees, you get a negative cosine. You move this back 90 degrees, you get a negative sine. You move this back 90 degrees, you get a positive sign. And so by tweaking this, which is kind of like the starting location on the ever repeating curve, you can get anything you want. I find this to be mathematical and unnecessary in this context. Okay, so we are going to put this function in to this equation, and we are going to see if it works. I need a fresh sheet of paper. Okay, so let's recap. What's our equation that we're going to put it into? We're going to put it into minus k over m x equals d squared x dt squared. And what function are we going to put into that equation? We are going to put in x as a function of t is a cosine omega t. My omegas are getting a little squirrely. Okay, let's put it in. Over here, we're going to have minus k over m times a cosine omega t. On this side, we're going to take two derivatives. Now, the first derivative is going to come down here. This is a symbol for first derivative. And we're going to have a omega negative sine of omega t. Take the second derivative, and that's going to be negative a omega squared cosine omega t. So put that in here. We're going to have a negative sine omega squared cosine omega t. And this is proof that it works because we can cancel lots of stuff. The a cancels, pachoo, pachoo. The cosine omega t cancels, and all that's left is the fact that k over m, the minus signs cancel as well, has to be omega squared. So as long as omega is the square root of k over m, this is the solution. You know, that's actually more information than we got before. You see, on our previous incarnation, everything was in terms of this period, but we're not really sure how long that period is. But by analyzing the forces, we now know the period is going to be related to k over m. Let's see, how does that work? Let's take a look at this. Let's take a look at what we had before. We had a cosine, and let me change colors because that makes things more interesting. We had a cosine 2 pi t over t, and then that is being replaced with a cosine, and then we have in here square root of k over m times t. So these are the same as long as 2 pi over t equals square root of k over m. Okay, get the t to the other side, get the k over m to this side, and we're going to have t equals 2 pi square root of m over k. Hey, we just figured out what the period of the motion is. That's pretty cool. So let me just give you a quick recap because I'm going to put a cork in this one right now. But what we did is, and I'm talking about what we did under another way. Another way, this is the typical way to solve these things. You write down the restoring force. You make sure that it's linear. This is linear in the variable x. That means we're going to get simple harmonic motion. You put it, and restoring force will have a negative sign. You put it into Newton's second law. Then you write the acceleration as the second derivative. You create a differential equation. You solve the differential equation by guessing at what the solution would look like and then fitting the parameters. Notice that we got a bespoke fitted parameter omega, what this has to be. We did not get a bespoke A. The amplitude canceled out, and that's something we're going to have to get from the initial conditions of the problem. In other words, it's up to us what A is. How much did you pull the thing to the side? Did you pull a little? Did you pull a lot? But hey, listen, I want you to notice that A, the amplitude of the motion, is not in omega, the angular frequency, and not in the period. Mass and spring system has the same period of motion regardless of how much amplitude you use. That is interesting. Okay, like I said, I'm going to leave it here for right now. We'll come back to it, do some examples, and then try some other stuff.